In this section of the lesson, we're going to take a look at concentration, what concentration means, and if we can do a bit of a visual representation of what a dilute or a concentrated solution would look like. So as you can see, I've created two extremely stable beakers. I don't know if this one would stand on a table properly by itself. I think it would roll over. So this is probably not a regulation beaker over here. This one's got a bit of a flatter bottom. I bet you that one could stand up. And what we're going to do is we are going to dissolve 2 moles of sodium chloride in this one and 10 moles of sodium chloride into the right one. And we filled the beakers with the same amount of water. We put half a liter or 0.500 liters, 500 milliliters, however you want to chalk it up. They all mean the same thing of water in these beakers. And then we're going to add either 2 moles of sodium chloride for the first one or 10 moles of sodium chloride for the second one. And visually we should see what differences in concentrations mean based on this rudimentary diagram I'm about to draw. Now I'm just going to draw one of these ions for each mold that I dissolve in. So if I dissolve 2 moles of sodium chloride into my water, I'm going to have 2 sodiums or 2 Na pluses, and I'm going to have 2 chlorines or 2 Cl minuses. In the right beaker, we're going to dissolve 10 moles of sodium chloride using the same rules. And you can imagine where we're going to run into some problems here. So let me start putting them on. So Na, I'm going to alternate back and forth from NAs to CLs. So that's 1 of each, 2 of each, 3 of each. Kind of fast-tracked that video there for you. But as you can see, when we dissolve more moles of sodium chloride into water, we end up with what's called a concentrated solution. And you may have heard this term specifically related to like acids and bases. Concentrated acids and bases are much more reactive, much more corrosive. They're more likely to react with metals and organic tissue because they are highly concentrated. Like our stomach acid, which is a concentrated acid that's there to basically break down all of the organic matter that our bodies take in when we eat. Now, if our stomach acid is diluted, like this guy over here, then it loses its corrosive power. Now, this is sodium chloride. We're talking about salt, not an acid in this case. But nonetheless, you can apply the same theory to this. And you can see that this is a much more diluted solution. If you were to take a swig of this, which you should never do because it's in a non-regulation beaker, then you would get a much less salty flavor from the water with salt in it here than you would if you took a swig of this guy over here that is absolutely ram-jammed full of sodium cations and chlorine anions. Now, when we're calculating the concentration of these things, concentration is calculated by dividing the number of moles that you've dissolved into the water, or whatever the solvent is, by the volume of the solvent that you've used, in this case 0.500 liters. So if I were to figure out what the concentration of this one was, well, I dissolved 2 moles per 0.5 liters of water, and that would give me a concentration of 4 moles per liter. Okay, this is the unit that we use for concentration, and it's essentially a numeric value of how many moles there are in the water for each liter of water that's there. For the one on the right, we've dissolved 10 moles of solvent, or salt rather, into the water. Now this is the formula that you can use for concentration. It's the one you're going to see in the textbook. N over V. N means moles, V means volume. Volume should always be in liters for concentration. It's a standardized unit, so everyone in the world uses the exact same units for it so that we can, as scientists, communicate more easily together. Now in this case, we have 10 moles per 0.5 liters because it's the same amount of water, and that's going to give us a 20 mole per liter concentration of salt into the right beaker. And that makes sense. We've put 5 times as many moles of salt in the water, so we've gotten a 5 times concentration out of the equation when we're done. So we're going to do one quick question about concentration and how we can use it. In this case, we're going to have to use a little bit of a unit elimination, much like the last question from the lesson. Yeah, I know we're getting a little bit back into unit elimination. I'm sorry. I know, you probably were already sleeping soundly knowing that we'll never have to go back to that horrific math and science stuff again. But if you ever work in a lab, this is something you're going to use quite often. And I hope some of you guys do decide to go on and learn a little bit about, how cool it is to work in a research facility and lab and report some of these things. And if you find that the math in this unit seems to suit you well, it might be a really good idea for you to get into that field, because it's a very, very interesting field if you're into research and learning new things and reporting the things that you're finding. So in this instance, we're going to dissolve 3.6 grams of solid sulfuric acid, there H2SO4, into 1.5 liters of water. And this question's got a little bit of a twist to it, and it has to do with the fact that the hydrogen has a 2 on it over here. Because what we're going to do is calculate the concentration of just the hydrogen atom. So we're going to kind of ignore the sulfate and instead just look at the hydrogen atoms itself. We already know when it dissociates, we're going to end up with 2 H pluses, and we're going to end up with an SO4 2 minus. Sorry, I just did a little bit of refocusing there, so it was a little easier to read. So there we go. That's the full dissociation equation of it. Now, before I go on, I'm going to calculate the molar mass of sulfuric acid, because if you guys remember from the lesson, the last question, I gave you the grams and asked you concentration. And we needed to figure out what the molar mass was, because when given the grams and trying to calculate concentration, we need to put it in terms of moles instead. So let's quickly calculate the molar mass. There's this molar mass there. Now, what I'm going to do is figure out how many moles of sulfuric acid that I have here. All right, to use unit elimination here, I know I've got 3.6 grams of sulfuric acid, and I'm going to multiply that by 1 mole of sulfuric acid divided by its molar mass of 98.0801 grams. That'll allow these to cancel out and should give me a 7 grams if I'm using appropriate sig figs, which I should because I've got 2 sig figs on there. My apologies, I just realized I wrote grams instead of moles. So let's fix that up. I'm sure none of you noticed that, right? Of course. Okay, anyways, the next thing we need to look at is what the question specifically asks for isn't the concentration of sulfuric acid, it's the concentration of the H plus ions in the sulfuric acid. So I can't just pop the 0.037 moles down here, because that's how many moles of sulfuric acid I have, not how many moles of hydrogen cations I have. Now, luckily, there's a really easy way to figure this out, because we can use stoichiometry for this. If there's 0.037 moles of sulfuric acid, and there's a 1 on the H2SO4, which there is, we're just not showing it, then if there's a 2 on the H pluses, that must mean that there's double the moles of hydrogen ions than there are sulfuric acid. Now, if you want to go through the unit elimination process of this, you certainly can. You can certainly go moles of H plus equals 0.037 moles of sulfuric acid. And then you multiply that 2 moles of H plus per 1 mole of sulfuric acid. Right? You can do the full unit elimination method, but you're going to notice that what you're going to end up doing is multiplying by moles by 2. You can do the full unit elimination method like I have here. You don't necessarily have to, because you're going to end up multiplying by 2 when you're done, right? So I can find moles of H plus by taking the moles of sulfuric acid and multiplying it by the stoichiometry ratio of 2 to 1. But if you just look at the numbers in the equation, you could see that for each mole of this, you're going to get 2 moles of that. So there's going to be double that amount, which is 0.074 moles of H plus ions. Now I have to use that number in my answer. So let's put the 0.074 moles up here. And we're going to divide that by the volume. Now, this has never changed. It's still 1.5 liters. So that's the same as it's always been, which is kind of nice. End up with 0.049 moles per liter. Now, for those of you guys who appreciate some brevity, you can shorten that unit to 0.049 and then just use a capital M. And that's the IUPAC generally accepted short form for moles per liter, moles meaning molarity. And molarity, again, as the name might suggest, it's not actually a Sherlock Holmes villain. It is, in fact, a measure of how molar or how many moles per liter there are in a certain solution. In chemistry labs, we use solutions like this all the time. When we make acids and bases, we usually start with a very concentrated solution of acid or base that's already made up, and then I add a certain amount of water to it to get it to the concentration or the acidity or basicity level that I want for whatever lab or activity that we're doing. So you may see this term quite a bit if you go to college, university, and do a lot of chemistry stuff, because solutions are a really big part of a lot of lab work that you may or may not end up doing in the future. Okay, that's the end of this week. Don't forget, there is a quiz this week. It's a short one because I know I've given you guys an assignment to work on. For your quiz, you're just going to be doing one concentration question. For now, just work on your My Pet Element assignment. Get your quiz when you're ready. Again, one question, calculate the concentration. Should be nice and straightforward for you. As always, if you have any questions about any of these materials or you want me to go through any of these with you one-on-one, drop me an email anytime. I'm glad to help whenever you need it. Have a great week and weekend, and enjoy the nice new beautiful weather we're getting.